All right, so let us now focus on modeling competition between two species. Well, so you might think of something like tigers and leopards in the same forest. So we are going to model it by the following system of differential equations with some positive coefficients. And I hope from the previous quiz you have learned that while the ecological meaning of these coefficients, so epsilon 1 and epsilon 2, are the intrinsic growth rates. Oh, sorry, it doesn't intrinsic growth rates. Then these two terms, sigma 1 and sigma 2, they model the competition within each species. So I will just write within. So meaning that this is the competition that restricts, that prevents the population from growing unboundedly, right? And then these two terms, minus alpha 1 xy and minus alpha 2 xy, they model the bad influence of y on x and the bad influence of x on y, respectively. So they model the competition between the species. So between the species. Okay. And we're going to go through a few specific examples, specific numeric examples of um, what it means, well, what kind of critical points we have and what it means in terms of the population ecology. So the question in all of these examples is whether the two species are going to coexist or if one of them is going to be exterminated. Because you can imagine that if they compete for the same resource, then what may happen is just logically is that they, if the competition is not too strong, then they will compete for the same resource. So they maybe that they will eat the same type of, I don't know, forest deer or whatnot. But then if the food is sufficient for the both and the competition is not too fierce, then they will, their population is just going to stabilize. The only thing that the level, the stable level of populations is of course going to be smaller than the intrinsic carrying capacities, right? Because we have the competition, because they have to compete for the same resource. But logically, what could also happen is that the competition may be in favor of one of the two species. If, say, one of the two species is superior to the other one, then their bad influence on the other one is just much stronger than the reciprocal bad influence. So then the species that is superior is always going to win the competition, regardless of the initial populations. And the third possible logical alternative is that one of the species is going to be extinct depending on the initial population, right? So if, say, there are many more tigers initially in the forest, then they will outcompete the leopards. Or if there are many more leopards, then they will outcompete the tigers. So let us see how we can determine which of the three alternatives is actually realized in each specific numeric example. All right, so coexistence means that there would be an equilibrium solution with both species present, right? So equilibrium solution, so we are looking for equilibrium solutions where x is positive and y is positive. So notice that in any case, if either x or y is 0, then there will be equilibrium solutions. So the first of them is just 0, 0, and the other one is when one of the species is at its carrying capacity and the other one is at 0. So let us now, assuming that at the equilibrium both of them are non-zero, so here we can cancel by x, and in the second equation we can cancel by y, and then we get a system of linear equations on just x and y, and then So it is a linear system, so that there is just one answer. So here it is 28. So, and coexistence would mean that 28 has to be a stable equilibrium. So let us see. Yeah. So there are three other equilibrium solutions. So there, so this 28 is here. At the same time, it's possible that one of the species is at its carrying capacity, and the other one is extinct. So it is these two equilibria, or if just both species are absent from the system. Yeah? But the interesting one is where both of them are positive, so it's 28. All right, so here, by the looks of it, you see that it is a stable equilibrium. So it seems that regardless of the initial condition, so eventually all trajectories converge to this stable equilibrium. And we see that these species are going to coexist. So now let us see if we can confirm this theoretically. All right, so let us find the Jacobian matrix. So here is the Jacobian matrix, and then by letting x, so now by letting x be 20 in this matrix and y be 8, we can compute the specific matrix, and then we can find its determinant, its trace, and the discriminant of the characteristic polynomial. Since the discriminant of the characteristic polynomial is positive, it means that we have real eigenvalues. Determinant positive means either both positive, both negative, and trace negative means both are negative. So it is an asymptotically stable node, and therefore the species will coexist, and the population levels are going to eventually stabilize at 20 for x and 8 for y.